Hi, I am Muniba Asif, and today I will be presenting Adversarial Data-Augmented Resilient Intrusion Detection Systems for Unmanned Aerial Vehicles. The outline of this presentation is as follows. First, we highlight the research objectives, then we delve into the research motivation. Further, we illustrate the most commonly reported attacks on UAVs, present the problem formulation, propose a solution, present a case study to validate our hypothesis, discuss the process flow of the proposed solution, and finally, we evaluate it and conclude. So the main objective behind this research is to analyze whether the existing defense systems for unmanned aerial vehicles, such as intrusion detection systems, are they resilient enough or not when faced by adversarial attacks? After a comprehensive analysis, our aim through this work is to enhance the resilience of these existing defense systems, such as intrusion detection systems, in the face of these adversarial samples. Let's have a look at the application of unmanned aerial vehicles or UAVs and some statistics. UAVs are not limited to one particular domain. Instead, they have multifaceted applications. For example, they are used in disaster management, for example, taking pictures in a volcanic eruption site. Not only that, they're also used in electric power grid inspections, defense and military operations, and precision agriculture. So the UAV industry is projected to grow up to $91.23 billion by 2030. Given the criticality of their missions, attacks on UAVs can have severe consequences. For example, mission interruption or a physical interception of the UAV or hijacking. Owing to the nature of its applications, security is extremely important for UAVs. As the main goal behind this research is to enhance resilience of existing defense systems against adversarial attacks, let's have a look at some real-life adversarial attack instances. For example, as reported by the New York Times, a Microsoft-created chatbot was manipulated by the adversarial attacks to let out racist and harmful comments. Furthermore, researchers also modified the audio input to a CAPTCHA and broke it. That the CAPTCHA was used for Google and Facebook. Let's have a look at one of the most commonly reported and investigated attacks in UAVs, the GPS spoofing attack. This is a UAV, and this is the flight path that it is supposed to follow. In order for the UAV to go from its current location to the target destination, this will be the movement. However, if an attacker is in between the satellite sending the GPS coordinates to the UAVs, even though these are the actual coordinates or the actual location of the UAV, the attacker will fool it to believe that it is instead here, which are the wrong location. And from this location to go to the target destination, the UAV will make a leftward movement. However, in reality, what is happening is that the UAV from its original location, instead of going to the target destination, is deviating from its trajectory. This is a GPS spoofing attack that we simulated using JMAVSIM simulator. As can be seen, this is the planned trajectory, and upon the attack, this is the deviation from the original trajectory. So what is the existing detection mechanism for this, and what is the research gap that this paper seeks to address? To answer these questions, let's have a look at the problem at hand. The current existing detection mechanisms for attacks in UAVs are machine learning based intrusion detection systems, or IDS. These machine learning based IDSs learn on the existing data distribution. However, comprehensive UAV data collection can be challenging because the flight data, let's say under a disaster management flight, will be different as compared to the flight data in a precision agriculture scenario. Hence, the collected data is sparse and limited, which leads to having inaccurate boundaries and which can further lead to false positives and false negatives as illustrated in the further slides. These inaccurate boundaries can lead to both false positives and false negatives. False positive in the case of an IDS for UAVs means a normal data point that is classified as an attack or a malicious point by the IDS. So just because the IDS does not have the learning or the data for that normal point, and this is its boundary, if anything, let's say a correct or a normal GPS data point lies outside this boundary, it will be classified as an attack, even though it was a normal data point. Similarly, this similarly is the case for the false negatives, which means an attack that was classified as normal. Again, just because the boundaries are not accurate and the data is not complete, the IDS fails to classify the point correctly. This vulnerability can be exploited by an attacker who can craft benign-looking adversarial samples to fool the IDS and yet still carry out the objective of GPS spoofing as illustrated above. So what is the proposed solution against such a scenario? So we identified that the problem is the sparseness and the limited data, less accurate boundaries. So what can be done is that we can use a generative adversarial network or some kind of augmentation technique to have more data, which will lead us to have a tighter boundary. Furthermore, the adversarial samples, benign-looking adversarial samples, will be taken into account to improve the learning of the IDS. Here, we mean that the adversarial samples will be used as a regularizer, which means it will prevent the IDS from overfitting. So how can an adversary craft these adversarial samples? It's very simple. What the adversary has to do is to add a perturbation to the original GPS sample. This perturbation is controlled by a threshold or epsilon, which basically constrains the perturbation to be in a limit that does not make the sample look like a malicious sample, and it ensures that the adversarial perturbation is stealthy and it evades the IDS detection, hence causing a misclassification, that is, an attack which will be classified as a normal point because the IDS fails to detect it. Adversarial samples or attacks evading the IDS can have the following consequences. The benign signals can be labeled as attacks. In such a case, unnecessary countermeasures will be triggered which will disrupt the mission. Furthermore, if the attack points or the malicious signals are labeled as benign, then no corrective actions will be taken even though the attack is taking place. These undetected attacks will jeopardize the safety of UAV and compromise the mission. So to achieve our goal, we built an IDS for UAVs based on machine learning. We use an autoencoder as our base model. The working principle behind an autoencoder is that it learns from its input data representation, aims to reconstruct it, measures the reconstructed error, and as a feedback, so it is actually reconstructing the data points as closely to the input as possible. This is used as a one-class classifier, which means it is based on benign learning only. Whatever is outside the benign learning space is classified as an anomaly, which means in terms of reconstruction error that a normal data point will have a low reconstruction error, hence it will be classified as normal, and an anomaly will have a higher reconstruction error which will exceed the threshold, hence it will be classified as an attack. So in order to analyze the impact of the adversarial attacks on the IDS, we carried out two adversarial attacks on our data to input to the IDS. Number one was the fast gradient sign method attack, in which the perturbation or the perturbation added to the original sample aims to increase the loss of the model. The second method, projected gradient descent, which is an iterative version of FGSM, is more stealthy, such that it adds some changes to the input data, measures how far it is from the original. If it is too far, it adjusts it back so that it is within the allowable range. As can be seen on the right-hand side are the FGSM attacks with epsilon or perturbation 0.1 and PGD with epsilon 0.35. So to analyze the impact of these two attacks, we varied the epsilon or the perturbation amount and the mix ratio. Mix ratio here means the amount of benign and adversarial samples in our test dataset. As can be seen that PGD or projected gradient descent causes an immediate significant decline in the performance even with smaller epsilon and smaller mix ratio. FGSM also depletes the accuracy of the model but slower than PGD. Coming back to our proposed solution, which includes augmentation using generative adversarial networks and utilizing adversarial samples as a regularizer, this is the process flow mechanism. First, we use GAN training, which includes a combination of InfoGAN and WGAN to produce synthetic samples that are as close to the realistic data as possible. By this, we get an augmented data set using which we retrain our autoencoder based IDS. Also, we include the adversarial samples as a regularizer, which help prevent overfitting for the IDS. Hence, we have a regularized autoencoder model. To analyze whether our proposed solution augments the resilience of the IDS for UAVs against the adversarial samples, we had these 4 research questions, which we answered in the following slides. For all our evaluations, we utilized 3 models. The original model with just the autoencoder based IDS, the GAN data augmentation in the autoencoder based IDS, and thirdly, GAN data augmentation along with the use of adversarial samples as a regularizer. We tested all three IDS models under the FGSM and PGD attacks. As can be seen that under FGSM attacks, the GAN data along with the adversarial sample based IDS performs the best. For PGD attacks, both GAN data augmentation and the GAN data augmentation, including the adversarial samples as a regularizer, improves the performance as compared to the original model. Secondly, we carry out an ablation study to see whether GAN data augmentation alone is sufficient or there is a need for using adversarial samples as a regularizer. As can be seen on the graph on the right-hand side, for FGSM attacks, the performance with just GAN data augmentation improved up to 68%, the model classification accuracy or the attack detection. However, using adversarial samples as a regularizer further improved our performance to 94%. Under PGD attacks, both GAN data augmentation and the regularization performed the same. As the autoencoder based IDS works on reconstruction error, we used MSE or mean squared error as a metric for the reconstruction error. We measured the MSEs for all 3 models, the original autoencoder based model, GAN augmented, and GAN plus adversarial samples as a regularization augmented IDS. We can see that the third one has the lowest and the smallest MSE values ranging from 0.0023 to 0.0021, which means that it most accurately reconstructs the original data as possible and is the best fit. Lastly, we tested all these models on real-world GPS spoofing attacks to measure the performance. All 3 models performed and detected the GPS spoofing attacks and the GPS jamming attacks very accurately. However, we noticed that using our GAN augmentation and the GAN augmentation with the adversarial samples as a regularizer, we see that we were able to decrease the false positive rate from 0.05 or 5.23% down to 1.54 for the GAN augmentation and further down to 0.42% for the final GAN augmented plus adversarially regularized IDS. For more evaluations, please refer to the paper and if you have any questions.